Hello everyone, and welcome back to Countdown to AP Week. This is day number 4, and it's a Thursday. Tomorrow will hopefully be Physics Friday. And today we have a cool little integral that I saw on Stack Exchange. And yeah, let's get to it. So the first thing I actually kind of want to note is this little natural log term right here. Because we saw in the last video that natural log of x plus 1 is equal to the sum from k equals 1 to infinity of negative 1 to the k minus 1 to the x times x to the k divided by k. But you'll notice that these have very similar structures, meaning that we can basically just kind of redefine our x and sub it into this equation right here. So when I say that, what I mean is we're basically going to say make x, instead of just being x, negative x to the 1 over n. And when we do that, what we get is actually the sum from k equals 1 to infinity still. The only thing that's going to change is the x. We have this negative 1 term and our k, but we end up getting a negative 1 to the k times x to the k over n. And you'll notice that our negative 1's actually cancel, except for this little bit right here. And this just means that we're going to have our sum, but it's going to be negative, of x to the k over n over k. And this is still from k equals 1 to infinity. So now that we have our natural log in terms of a nice summation, what we can do is just integrate this with respect to x and proceed from there. So what we're going to do now is apply the integral. So we have negative integral from 0 to 1 of our sum, x to the k over n over k from k equals 1 to infinity dx. And similar to the last video, which I keep referencing, we can just move the k's outside. We cannot do that. I'm sorry. I was assuming there's an integral there. We can reverse the sign. We can reverse the order of the summation and the integral, and then just pull the k out of the integral because it's a constant. Goodness, yeah, don't pull the k outside of the summation. That's a big no-no. Don't do that. Goodness. Oh my. Anyway, we have our sum from k equals 1 to infinity, 1 over k, and then times the integral from 0 to 1 of x to the k over n dx. And this is a relatively simple integral to evaluate. We're just going to apply, the usual reverse power rule. What we get is just negative sum again from k equals 1 to infinity. I'm just going to omit the bounds from now on, I think. But what we have is a 1 over k, and then also the denominator a k over n plus 1. And that just comes from this integral right here. But what I'm going to do is actually multiply the top and bottom by n real quick, just to kind of get the n over here. So what we get is, again, the negative summation of 1 over k, and then we have an n out front, meaning that we have a k plus n right here. And this really does not look very nice, and I thought the exact same thing when I was evaluating this. But actually, if we apply partial fractions here, it does become a little bit nicer, and we're able to apply some identities to it. So, let's take a look at this little bit right here. What we're going to say is just we're going to have sum a over k plus b over k plus n is equal to 1 over k times k plus n. And as such, we can just multiply both sides by k plus n, leaving us with a k plus n plus b k equals 1. And so all I have to do is just plug in the appropriate values for k and solve for a and b. So if we let k equal 0, for example, that looks more like a 6. Whoops. If we let k equal 0, then what we find is that a n, because that's going to be 0, a n is equal to 1, meaning a is just 1 over n. And if we let k equal, say, negative n, what we find is that our b right here, our b, is just equal to negative 1 over n. And this is usually how partial fractions go, at least with the nice ones like this. You get like, a is one thing, and then b is like the negative of that thing. But one thing that you might notice is that we have n's in the denominator, but we also have this n in the numerator. So when we distribute this, it does simplify quite a bit. So I might be jumping ahead, but all I'm going to do is just sub this in, and then we'll start crossing some stuff out and simplifying. So what this is right here then is we still have our negative n out front with our summation, but instead we have our a was defined to be 1 over n. So we have a 1 over nk minus our 1 over n times k plus n. And what we have is n's in the numerator, n's in the denominator, as I was just saying. We cancel all that out, make that positive, and make that negative. Meaning that our actual summation is just equal to, let's scoot the camera on over. Our actual summation is just equal to the sum of 1 over k plus n minus 1 over k. And this really does not look very nice, in all honesty. But there's one very, very important thing to note, and I will write this identity off to the side. I'll do this in pink. What we know is that the digamma function of some z plus 1 is equal to negative gamma, so that's the Euler-Mascheroni constant right there, and then plus the sum from k equals 1 to infinity of 1 over k minus 1 over k plus that said z. And you'll notice that the structure for these things is extremely similar. The only difference really is that, well, this is the negative of that right there. So if we were to just to say multiply, or I say multiply, we can just subtract this from both sides right here. So just kind of move that on over to the side with the gamma, and then move this gamma over to this side. What we have is actually just our answer. So doing that, we find that our sum, which I actually won't write out again, our sum is actually just equal to negative gamma minus digamma function of n plus 1. And yeah, that right there is just our answer. So this was a little bit of a shorter video, but I still hope all of y'all enjoyed, and I will see y'all tomorrow for Physics Friday. Adios!